Thank you. So my name is Daniele Cortis. I come from the Gran Sasso National Lab, that probably you know is the one of the biggest underground laboratory in the world, and is one of the laboratory of INFN, that is the Italian National Institute for Nuclear Physics. I work on the mechanical service, and I am the head of design, and I am the department. So a few words about our institute. It has a 5 research line, from particle to astroparticle, and of course we did a lot of technological research, among which there are medicine, cultural heritage, and of course additive manufacturing. So as I said, LNGS is one of the largest underground laboratory in the world, dedicated to neutrino science and astroparticle physics. And inside its mechanical service, the mechanical division, we can do all the stuff from the design to the material characterization, production, quality control, and of course testing. We have several technology, additive technology, from LPBF for the metal ones, or FDM, DLP, and other technology that can help us to cover the overall cycle of our design process. And we are also the leader of official INFN hub for additive manufacturing, materials engineering and research. So you can check our official website for more information. And we have several collaborations with Italian university, Italian Research Institute, for example, ENEA or CNR, and with other foreign institutions, especially in Japan, for material characterization with non-destructive techniques about, for example, neutrons. So the purpose of our research in additive belongs to several reasons. In our experiments, we deal usually with extreme environment. For us, extreme environment are very low temperature, so cryogenics, high temperature, for example, inside accelerator particle, or vacuum environment. All these extreme conditions are designed to reduce the influence of the external world to our experiment, our detector, for example, or to reproduce some specific phenomena inside our machine. So we need to develop specific high-demanding components with high-demanding material and with specific new technology. So LPBF, power-based fusion, is one of the most used technology for metal additive manufacturing that we currently use for produce, for example, target holder. This is aluminum target holder for an accelerator in our underground lab. It's like an heat sink, let me say. Also, there is, for example, a colorimeter produced with a multi-material approach, always with LPBF. And the last one is a beam collimator for our accelerator. So, so we start to study several different materials in the last year. One of the most important aluminum alloy that we found is it belongs to the family of the 5000 series with magnesium. And this particular material is called by the strength AL, strength aluminum, and is produced and supplied by Metals for Predictive company. That is an Austrian-German company. And it is similar to the scalm alloy, the well-known scalm alloy produced by the carpenter. And the main characteristics of this material is that during the solidification, it produces some nanoparticles, some aluminum, scandium, and zinc particles along the boundary of the melt tracks. And this gives to the material high strength and high thermal stability with the temperature change. And respect to the well-known scalm alloy, it has a slight percentage of scandium, for example. And of course, it's a material that requires a specific agent treatments to get the right mechanical properties. So we produce it with a standard LPBF machine, Prima Print Sharp 150, that is produced by an Italian company located in Turin. And here you can find the process parameter that we employ to the production. And we decided to realize two kinds of different species. The first one with a round cross-section to optimize the unmounting and mounting procedure under the low temperature and high temperature test. Another one with a flat cross-section to optimize the evaluation of the elastic property, so the position ratio and the elastic model. The specimens were located on our building platform randomly. As you can see, the direction of the gas, the powder, of course, the building. After the production of the specimen, we decide, of course, to do the aging treatment, and we do a wet tumbling on around the specimen in order to avoid the presence of some source of defects on the surface that could be affect the tensile results. And we were able to reduce the roughness, so increase the quality of the surface up to 1.5 microns, starting from about 5. Okay. So the tensile tests were done with a standard universal testing machine equipped with the environmental chamber with liquid nitrogen that is able to reach minus 150 degrees. And we've used a standard extensometer for the standard tensile test to get the mechanical properties up to rupture, so the yield strength and the ultimate tensile strength, and a big biaxial extensometer with 3 channels, 3 independent channels, 2 for the axial and 1 for the transversal strain, to get a better resolution, a better accuracy for the elastic models and the posture ratio. Thanks to this combination, we were able also to evaluate of course, the shear models. And here you can find some example of the plot that you can get from this extensometer type. So results. At room temperature, so 22 degrees, we find that the material possess the mechanical properties described by the supplier of the powder. So it confirmed the right PBF process to produce the material at a high relative density that we get, that is over 90%. But we also see that the material exhibit the PLC, the Portevin-Le Chatelier effect, that is produced by the dynamic aging. So the atom of solute inside the aluminum matrix in the dislocation increasing in creating a sort of serration inside the stress and strain plot, as you can see. And this kind of serration disappears at lower temperature because the PLC effect depends on the strain rate, temperature, and the density of the dislocation and the solid atoms. And at the lower temperature, so at minus 100 degrees, the mobility of the solute atoms are blocked, so they cannot pin any more dislocation. But with the closer magnification of the plot, we still see some observation just after the yield point of the material. So just a bit less little serration is still present. On the other hand, with high temperature, with the increase of the mobility of dislocation, the PLC effect was completely suppressed, and the material progressively loses its strength at 200 degrees. So we try to define the operative range of this material for our purpose. So minus plus 100 degrees probably is the range inside with the material can guarantee good mechanical properties and reliability. So talking about elastic modulus pressure ratio, it confirmed as expected. We calculate about 60-65 gigapascal for the room temperature properties. And of course, the elastic model increase with the decreasing of temperature. And on the contrary, the Poisson ratio starts from a lower value, and with the increase of temperature, it increases itself. So from 0.32 to about 0.40. After that, we checked the structure, the microstructure of the material. As you can see here, there is a double grain structure with the nanoparticles, aluminum, cadmium, and zinc nanoparticles on the boundary of the meltable tracks that give to the material the high strength, and the columnar grade inside the melt pool that follow the direction of the cooling rate. After that, we checked also with the scanning electron microscope the fracture behavior of the surface of the tensile specimen, and we find that at the lower temperature the material has a mixed fracture mode, but with high presence of ductive feature. And this kind of ductive feature are more present at, of course, room temperature. And we found also a very equiaxial dimples at higher temperature that confirm the plastic and the ductile behavior of the material as expected for this kind of alloy. So finally, we defined that for now, this kind of range of temperature could be good for the application for our purpose of this material. Of course, some defects that we find inside the refractory surface, for example, lack of fusion, can increase the stress concentration inside this defect, producing a low failure of the material in some cases, for example, reducing the elongation, the overall elongation of the material. Further developments will be certainly the test of material at lower temperature. So probably we can try to reach the minus 200 degrees in order to try to find and evaluate the ductile to brittle transition temperature, where it is located for this material, probably minus 150 degrees. And we want to try build an elastic constitutive model for this material to be implemented in our models. For example, for this kind of application, that is a thin-walled vessel that must withstand very high pressure, for example, 1,200 bar, of course, with a reinforcement of carbon fiber. And this is an accelerator target for the CERN. And of course, this thin-walled vessel should work at cryogenic temperature, so very low temperature, and in vacuum condition. So we need to have a reliable model to be put inside the simulation in order to guarantee reliable results and avoid any damage inside the CERN structure. So thank you.